Hi everyone, my name is Emily Kempfer, and I'm really excited to discuss with you all the improvements of multi-reference perturbation theory within the ORCA 6.1 release. Within past ORCA releases, we have had multiple multi-reference methods, like CASSCF, NEVPT2, as well as more computationally costly methods like MRCI and MRCC. Now, as we have wanted to continually improve the ORCA software, we created a wish list for improving multi-reference perturbation theory methods. So some of the things on our wish list are accuracy, which are greater than or equal to NEVPT2, as well as the possibility for handling larger active spaces, and a few other very important things like intruder state free, being numerically stable, as well as being size consistent. And we're very excited to introduce within the ORCA 6.1 release 2 new methods, specifically NEVPT4-SD as well as ICE-NEVPT2. Now first, going into NEVPT4-SD, NEVPT4-SD has accuracy greater than NEVPT2. It's also intruder state free, numerically stable, and size consistent. So NEVPT4 is a higher order perturbation. So NEVPT2 is actually equivalent to MP2 and really does not recover enough electron correlation. So higher order perturbations really are more desirable. However, it is known that third order perturbation can have a positive energy correction and deteriorate from experiment. So more accurate results can be achieved using a fourth order correction. Now NEVPT4 can be divided into 4 different terms for its equation. First, we have a doubles term in orange, triples in blue, quadruples in green, and a renormalization term in purple. Now, this current methodology actually does not compute the triples, quadruples, or renormalization term, and that is why we have dubbed this method NEVPT4-SD. So now, going into some preliminary calculations, we have decided to look at the diatomic dissociation energies of BH and N2 in comparison to a full CI calculation. Now, we have also done these calculations using MRCCSD as well to compare our methodology to another well-known methodology too. So the NEVPT4 methodology is shown in purple triangles and MRCCSD is shown in black circles. And we can see that the NEVPT4 methodology does do a very good job of staying practically parallel with the MRCCSD method. Now, this is of importance as we go later into this talk and see the computational timings between NEVPT4 and MRCCSD and see that NEVPT4 is significantly cheaper than MRCCSD, but with this we can show very similar accuracy. Now, another test set we looked at was in ethylene rotation. Now, this is an interesting molecule to look at, mostly because as the rotation goes forward, the potential energy surface does change. So at 0 or 180 degrees, the molecule has a very well-defined pi bond, which is formed by the overlap of the p orbitals on each carbon atom. However, as we get closer to the 90 degrees, the p orbitals are no longer orthogonal and do not overlap. So we actually have more configurations and more static correlation, which cannot always be described by the minimal 2-2 active space. So this figure here is a delta E graph in respect to MRCCSD, and we can see that NEVPT2 in green, NEVPT3 in blue, and MRCPA0 in gray all have this characteristic hump between the 70 and 110 degree angles. And this is mostly due to the fact that these methods cannot describe these additional configurations which are coming forward at this 90 degree angle. However, we see that NEVPT4, which is the purple triangles again, has practically a linear line, thus being able to describe this entire potential energy surface throughout the changing system. Now, looking forward at the efficiency of the methodology, we can look at how the NEVPT4 method compares to ICE-NEVPT2, which is known as a more fast NEVPT2 methodology. We can compare it to FIC-NEVPT2, which is the base for this NEVPT4 methodology. So SC-NEVPT2 is about 72 seconds, while FIC-NEVPT2 is about double that, which is what we expected. Now, NEVPT3 and NEVPT4 are both similar in timings, which are about 500 seconds, mostly because the most computational time is taken when calculating a U vector, which is done within the NEVPT3 step. Now, comparing this to the single iteration of MRC-PA0, we see that this also takes about 500 seconds. And this makes sense because the MRC-PA method also calculates this U vector, so it makes sense that it takes about the same amount of time. However, the MRC-PA0 method is an iterative method, so we can't necessarily only look at how much time only one iteration takes. We also want to look at how much time it takes for multiple iterations. So the total timing for an MRC-PA0 calculation is about 2,000 seconds. Now, comparing this to MRCCSD, it takes about 500,000 seconds. Now, previously we looked at how the NEVPT4 compares to MRCCSD, and we showed that NEVPT4 does show similar accuracy to MRCCSD. However, it is a fraction of the cost. So we can achieve very similar accuracy with little time. So how can you run NEVPT4 SD in ORCA 6.1? Well, it's very simple. First, all you have to do is run a typical CASA-CF calculation and include this FIC-NEVPT4 SD within the title line. And our output from these calculations will actually contain not just the NEVPT4 energies, but the NEVPT2, NEVPT3, and CASA-CF energies as well. So we can achieve all energies from a single calculation. Now, moving forward to the other new implementation within ORCA 6.1 is the ICE-NEVPT2. Now, this methodology does have accuracy equal to NEVPT2. It has the ability to calculate large active spaces. It is also intruder state free, numerically stable, and size consistent. However, when implementing this methodology, we did encounter quite a few issues with the idea of it being intruder state free. Now, you may wonder, how exactly can a NEVPT2 methodology not be intruder state free? Well, NEVPT2 is known to be intruder state free, but it mostly is due to the CASA-CF wave function that is being put into the NEVPT2 equation. So we assume that the dial Hamiltonian is an eigenfunction of the reference wave function, specifically which is coming from CASA-CF. Now, with this calculation, the dial's rank reduction scheme, it requires at most a fourth order RDM. However, when running ICE approximations, the wave function is no longer an eigenfunction of the dial Hamiltonian. And thus, when applying the rank reduction scheme, we're actually encountering intruder states. So how exactly can we fix this? Well, we can fix this by using something which we detail as full rank NEVPT2, which no longer assumes that the dial Hamiltonian is an eigenfunction of the reference wave function. However, this does require a fifth order RDM, but within our implementation, we were actually able to reduce the cost of this fifth order RDM, so it is not as computationally costly as one may assume. So when running ICE-NEVPT2, there are two key parameters which we need to look further into. So when running this calculation, first you have to run an ICE-SCF calculation and then read those MOs into the full rank NEVPT2 calculation. So two key parameters which are needed specifically for the full rank NEVPT2 calculation is a TGen and TVAR. So TGen is the threshold for configuration generation, and it controls the accuracy and size of the CI space. So a smaller TGen leads to a closer FCI result. However, we have to balance accuracy and cost when determining this value. So they found that the TGen between 10 to the negative 4 and 10 to the negative 3 actually balances the accuracy and cost within this methodology. Now, secondly, we have a TVAR, which is the threshold for variational selection. This filters the configurations based on the perturbative energy corrections. Now, a typical default for TVAR is TGen times 10 to the negative 7th, which is normally about 10 times 10 to the negative 11th. However, they found within these calculations that TVAR equal to TGen times 10 to the negative 3 is actually sufficient for a full rank NEVPT2 calculation, which also still balances the accuracy and cost of this methodology. So going further into some efficiency testing, we looked at the octacene molecule using a TZVP basis and a Cas 30-30 active space, so 30 electrons in 30 orbitals. They set TGen at 10 times 10 to the negative 3, and with this, they computed about 35,000 CSFs in the ICE CI reference wave function and about 866 million CSFs in the RI CSF space. Now, this calculation took about 33 days using 20 cores, which is a fantastic feat for how large this active space is and how many CSFs were computed in this calculation. So how exactly can we run ICE-NEVPT2 in ORCA 6.1? Well, first we run an ICE CASA-CF calculation shown within this first block. We then run an ICE-NEVPT2 calculation with the converged MOs from the ICE CASA-CF calculation. It's very important that we read in those MOs from the previous calculation into the second one. Now, there are a few extra keywords that I want to point out which are very important for these calculations. First, the ActOrbs unchanged keyword. The active space is incomplete, and keeping up with other approximate FCI methods, these rotations of the active space are neglected and thus important for convergence. Now, two other keywords, the CAS-CI approx true, as well as the D4 step fly within the second calculation. The CAS-CI approx true sets the full rank NEVPT2 calculation to make sure that we're running it intruder state free ICE. Now, secondly, we have the D4 step fly. Now, this is not default, but it is sometimes necessary depending on the active space which is chosen for your CASA-CF. So when running a very large active space calculation, it is necessary to set this, mostly due to memory constraints. I want to thank you all so much for your time and for listening. I want to thank Dr. Professor Frank Neza for all of his support and encouragement in these projects, as well as Kanthan Civillingham, the Max Planck Society, and the ORCA team for all of their hard work within the ORCA 6.1 release. I'm looking forward to seeing all of the interesting research being done within the ORCA 6.1 software.